Hello and welcome to my presentation, Coastal Zone Sea Surface Temperature at 100 metre resolution. My name is Chris Merchant. I'm at the University of Reading and I'm part of the National Centre for Earth Observation in the United Kingdom. And in this connection, I'm really thinking about how perhaps in future years of the Sea Surface Temperature Climate Change Initiative that I lead, we'll be able to perhaps make products at high resolution from upcoming missions, such as the Trishna mission. There are various reasons why deriving sea surface temperature in coastal zones can be more challenging than in the open ocean. There can be greater spatio-temporal complexity around the coasts, and of course we have to deal with an irregular coastline, which in the lower resolution sensors is of course not very well resolved. And we may also have to deal with features such as coral reefs, which have their own issues. And so GRIS products based on observations that are of order a kilometre in resolution don't necessarily capture coastal zones all that well. But we know from missions such as Landsat and EcoStress that with higher resolution there is potential to say a lot more about coastal zones. And in that regard, the upcoming missions such as Trishna will be a step forward, a great advance. And for this reason, in SST-CCI and other projects, we're beginning to look forward to what might be possible with Trishna and other missions. The Trishna observations will be a level 1C product of brightness temperatures, resampled to 60 metre resolution, and will happen at a good time of day and night, close to the peak of the diurnal cycle. The Trishna acquisition mask, as seen here, covers shelf seas and a good halo around the entire coastline of the land masses. And so this will enable coastal zone observation, which is great. But in general, sea surface temperature is a different challenge compared to the land surface temperature, which is the main focus of missions like Trishna. Particularly, the requirements are somewhat more onerous. So around the coastal zones, I suggest that we need to be able to resolve well temperature contrasts of order a Kelvin. And in the SST world, we are used to biases that are rather small, preferably of order 1/10 of a degree or better. In this presentation, I'm focusing on the Trishna mission as a particular case study for high resolution SST, because it's going to be the first mission that we have access to. Trishna will have 4 spectral channels shown here, and also in the background of this plot you see the transmittance between the surface and the atmosphere, also as a function of the wavelength. The new channels, as with the traditional split window channels at 10 and 11 micrometers, do provide differential sensitivity to variations in water vapor in the atmosphere, which is what we need for retrieval. Here is a little bit more information about the thermal infrared channels on Trishna, bands TIR1 through to 4. In particular, the table shows the uncertainty characteristics. There is the NE delta T, which is the uncorrelated noise in each of the channels, which ranges between 0.2 and 0.25 Kelvin as an expectation, as a requirement. And then there are the calibration requirements, which are shown in the right 2 columns. The absolute uncertainty, or the uncertainty in the absolute calibration of the channels, is required to be less than half a Kelvin. And there's also a specification to do with the relative uncertainty between channels, so the interband values on the right hand column of 0.3 Kelvin. So for the purpose of this study, to understand what this table of specifications means, I've transformed those requirements into the error covariance matrix that corresponds to those uncertainties. So an error covariance matrix tells us down the diagonal of the matrix about the effects that are not correlated between different channels, and the off-diagonal terms represents correlations in errors between channels. Now, satellite data is quite complicated. The usual separation of types of errors that we have in the laboratory, which is just random and systematic, is not adequate to describe satellite data. And this was explored in quite a lot of detail in a project called Fiducio. And the simplest way of describing satellite data is to decompose the errors into those that are uncorrelated between all observations, those that have some sort of structure, and those that are fully in common between all observations. If you want to read more about this decomposition of the errors in a satellite observation, I refer you to the paper that's shown. So this table of specifications corresponds to the error covariance matrices shown on the slide. The first one is the diagonal matrix that represents the noise. The second term captures the fact that some of the calibration errors will be different between channels according to that specification. And the final term shows the amount of uncertainty associated with errors that are going to be in common between all 4 channels, as implied by those specifications. So armed in this way with knowledge of the spectral response functions, which means we can do simulations within a radiative transfer model, and armed with knowledge of the error covariance matrices just shown in the previous slide, this study is a simulation study of what sort of retrievals might work well for coastal zone SST in a reprocessing context. The simulation study is based on a relatively small sample of profiles, but which is adequate to explore the situation. So we have a range of sea surface temperature across 37 profiles, ranging from just above freezing up to quite warm tropical temperatures. And we also fully explore the range of atmospheres, from quite dry atmospheres, so quite low total column water vapor of 4.5 kilograms per square meter, up to more than 60 kilograms per square meter of water vapor in the atmosphere. We'll be looking at both scene mean SST retrieval, plus also retrieval, how well the retrieval works to capture variability within a box. And the true variation in SST that is applied relative to the scene mean temperature for every profile is shown in the lower right-hand plot. So we'll be looking at how different forms of retrieval capture this variability. And this variability has a range between minus 0.5 degrees and plus 5 degrees. So it's a variability of a range of a Kelvin. I've also imposed the full range of Trishna satellite zenith angles variation across the pixels across the track, which is artificial in terms of the change of zenith angle per pixel, but just to capture that full range of retrieval zenith angle. For each profile across the scene, I simulate a prior, so an expected variation in brightness temperature, the true brightness temperature if we were able to observe it perfectly, and also observed brightness temperatures, which are brightness temperatures including calibration error and noise. And those are shown on these 3 diagrams here. We see that with a constant prior SST for the scene, which is uncertain to the level of a third of a Kelvin, and also with constant atmospheric water vapor content, which has a prior error of about 10%, we get the smooth variation of brightness temperature across the track, corresponding to the imposition of the varying satellite zenith angle across the track. The middle image shows the variation in SST and how it translates into brightness temperature for the case of TIR1. And then when we add noise, we see that that pattern is quite significantly improved. So noise is going to be an issue. Thinking about what options we have for retrieving SST from an instrument like Trishna, because there are split window channels, we could do a traditional coefficient-based retrieval such as the NL SST. but in my opinion that will prove to be unnecessarily noisy. And just to show you the level of noise we get from NLSST, that's illustrated in the pictures below with a true spatial variation and what NLSST noise would do to the retrieval across that scene. For operations, I understand that over the sea the SST will be retrieved using temperature emissivity separation. This method retrieves both emissivity as well as temperature, as is indicated by the title of the method, but it doesn't therefore take advantage of, or doesn't necessarily take advantage of, the a priori emissivity constraint. So I'm going to be exploring a physically based retrieval, a form of optimal estimation. In optimal estimation, we use the difference between the expected brightness temperature, so the prior brightness temperature, and the observations to infer how to nudge the prior sea surface temperature towards a more accurate value. First of all, I'm going to look at how this does in terms of SST bias across the whole scene. So I'm doing scene average SST retrievals. The brightness temperatures are adjusted with simulated errors consistent with the error covariance given the specifications we saw earlier. And in order to expose the full impact of those calibration issues, I'm using a very weak prior SST constraint in this case of a large uncertainty of 7 Kelvin. So when using just the split window channels, that's 11 and 12 micrometer channels, typically the SST bias is almost a Kelvin, and it's not much smaller when we're using all 4 channels, although there is a bit of averaging out of different calibration errors across the 4 channels, which does produce a lower SST bias of about 0.7 Kelvin. So it's clear that these are biases which are larger than we're used to in the SST world, and that bias correction will be necessary for an instrument specified to the standards of Trishna. For the remainder of the talk, I'm going to assume that bias correction has been successfully done and use brightness temperatures that are free of calibration bias, and focus on how to retrieve pixels using optimal estimation once bias correction has been undertaken. So here are the results for one example location, a middling case across the sample of 37 profiles. And this is per pixel optimal estimation undertaken using 2 channels as shown in the top left, or all 4 channels available shown in the lower left. Both retrievals come out quite noisy. The noise is a little bit less when using 4 channels, as we'd expect, because the availability of more brightness temperatures beats down the noise a little. Neither of them is fantastically good at representing the full subtlety of the true SST example shown in the top right, but nonetheless this is a promising first result. Having looked at the retrieval for one particular location, these graphs show the performance across all the locations, looking at the scene average performances. The left-hand column shows the scene average retrieval error for the 2-channel and 4-channel per pixel retrievals, and the right-hand column shows the noise within each scene, the uncorrelated uncertainty in SST. As we might expect, there is a small benefit from using 4 channels rather than 2, in that it suppresses some noise, seen on the right-hand side, and there's also some bias reduction from averaging out, or from better treatment of the atmospheric correction. But nonetheless, the amount of noise we're getting here, the standard deviation of the SST errors shown on the right, is getting up to almost half a Kelvin in the wetter atmospheres, which is really somewhat larger noise, level of noise, than we'd ideally like for SST, because it wouldn't allow good representation of the small-scale variability in the coastal zones. In order to explore how we might beat down the noisiness of the high-resolution sea surface temperatures, I turn now to an experiment where we've done a smooth atmosphere version of optimal estimation. In a smooth atmosphere optimal estimation, we retrieve the SST not for a single pixel at a time, but for a localized area of clear sky pixels all in one go. And these are associated with one common retrieved amount of water vapor content across all those pixels. And this is justified because the length scale of SST variability is likely to be shorter, especially in coastal zones, than the atmospheric variability, which can be assumed to be constant over scales of several hundred meters. The effect of the smooth atmosphere assumption is to disambiguate the noise from the water vapor content effects on SST. And as a result, this drives down two forms of error. It drives down the SST noise, but as I've realized in this study, it also drives down the propagated error from the error in prior water vapor. The improvement from the smooth atmosphere approach is particularly useful, I think, for high resolution SST. You've seen the picture on the top left before. This is the 4-channel per pixel optimal estimation result. Below it is the smoothed version, in which the variability in true SST that's also shown is much more cleanly resolved than in the per pixel version. You can also see in the table that the scene level noise across this particular example is significantly reduced by about a third. And the sensitivity to real variations in SST in Kelvin per Kelvin is almost 98%, which is very close to the target we would like of a 1-for-1 sensitivity to sea surface temperature variations. Looking at the statistics across the 37 profiles, if I start on the right, you can see the expected reduction in noise applies right across the full range of total column water vapors that are in the sample. So the smooth atmosphere technique does greatly reduce SST noise as expected. But equally striking is the degree to which it reduces the scene mean biases, which are shown on the left. So remember, this is simulating having done bias correction. So these biases in the top left-hand plot don't come from calibration issues, but come from the limitations of the retrieval. And these are greatly reduced when we go to a smooth atmosphere version of optimal estimation. Now, although we developed smooth atmosphere optimal estimation over 10 years ago, I hadn't realized until this study this effect of improving the bias as well as the noise. It's quite obvious that smoothing out the retrieved water vapor variation will obviously help noise. But why does it help reduce bias? Well, it's because the prior water vapor has an error, and the disambiguation of that comes from having a single water vapor retrieval across all the pixels helps reduce that prior error. So on the left-hand diagram here, we can see that if we retrieve per pixel, a significant correlation exists between the average SST error across the scene and the total column water vapor error that was used in the simulation of the prior brightness temperatures. Essentially, when it's the per pixel, there isn't enough information to correct this total column water vapor error very well. But when we're doing several pixels together with a common water vapor retrieval, there is enough information to reduce the error in the total column water vapor, and that at the same time improves the SST error, and that's what's shown on the right. So in summary, although we're very excited to look forward to the Trishna mission, and it will be a great opportunity for improving our understanding of coastal zone sea surface temperature, the noise and calibration biases of this mission will be larger than the SST community is generally used to. So we will need to address that in our sea surface temperature retrieval algorithms. And it's clear that reducing bias in SST noise to levels that will be useful for coastal zone SST will require us to do bias correction and also to adopt low noise algorithms. I've presented a simulation study using bias-aware smooth atmosphere optimal estimation, which shows some promise. The conclusions for the study are that we need to use all 4 channels because that helps reduce the noise, that we can achieve sea surface temperature noise that ranges between 0.1 and 0.3 Kelvin across a range of dry to wet locations, which is very promising, and that smooth atmosphere optimal estimation is a way to do this, which both reduces the noise levels, which we knew before, but also is a way of reducing some aspects of the bias in the retrieval, which is a new insight.